We're pleased to have for our next talk on indirect searches for dark matter, Tracy Slatyer from MIT, and I'll let her take it away.
Thanks very much, Tim, and thanks very much to all the organizers. I'm very happy to be here. I don't have quite as long a history with TeVPA as some of the previous speakers, but I think 2009 was my first one. It was one of the first major conferences I ever went to, so I'm very pleased to be here. So I was asked to tell you about indirect dark matter searches in 25 minutes, which is a bit of a heavy lift. So what I'm going to try to do here is point you to all the many, many very interesting talks on indirect dark matter detection that are going on in the parallel sessions, while giving you a summary of where we currently stand with constraints on dark matter annihilation or decay, and then a brief introduction and status update to the anomalies that you will hear about in more detail in subsequent plenary talks and in the parallel talks, if you make it to them. So first, what are we talking about? Well, don't need to explain it to this audience, but we have pretty good evidence that dark matter constitutes about 80% of the matter in the universe. We would like to know what it is. So far, all our evidence comes from gravitational methods, and there will be some really interesting talks later on what you can do just by looking at the distribution of dark matter in our universe. But if you want to try to figure out how it works with the standard model, there is a long history of looking at this in basically 3 ways. So indirect detection, which is going to be the focus of my talk today, we're looking for standard model particles produced by dark matter interactions. Direct detection, you look at the scattering of standard model particles from dark matter. Colliders, you try to produce the dark matter particles. Or, in my preferred mnemonic for this, you can break it, shake it, or make it. So today we'll be focusing on the break it mechanism. Now, I should mention, I'm not really going to talk today about axion searches because that's worthy of a talk entirely on its own. In that case, you should think about the dark matter as behaving like a coherent field, not as a particle. There, I will just point you to these talks in the parallel sessions on axion dark matter and the various experiments that you might use to look for it. But if you didn't, and I'll also mention, again, I'm not going to go into much detail on this, that there are some very interesting mechanisms that sort of span the boundary between direct and indirect detection, and they sometimes get left out in these talks where we're trying to put things in little boxes. For example, you can have the mechanism of direct detection where dark matter scatters off standard model particles, leading to what you would usually think of as indirect signatures that you look for with telescopes. Scattering could heat or even destroy astrophysical bodies. There are some talks by that in the parallel sessions by Tsai and Raj, and you can potentially get very strong probes from this. Elastic scattering between dark matter and visible particles could possibly leave signatures in cosmic rays. You can also turn around the other way, although this won't be so represented at this conference, and have an indirect detection mechanism where the dark matter annihilates, but then you look for the dark sector products of that annihilation scattering off standard model particles. And you can also have cosmologies where it's the scattering, not the annihilation, that primarily determines it. But most of my talk today, I'm going to focus on classic indirect detection, where the mechanism is the dark matter decays or annihilates into either standard model particles or something that eventually decays to standard model particles. And then we look for those annihilation or decay products in order to try to reconstruct what the dark matter is doing. Why do I say annihilation or decay? Well, very generically, we don't know how dark matter interacts with the standard model. You can classify the possible processes by saying how many dark matter particles do you have in the initial state? Is it 1, is it 2, or is it more? In general, because the dark matter densities for non-axion dark matter are pretty low in the present day, if you have 3, you may well have processes with 3 or 4 dark matter particles in the initial state, but they're usually quite suppressed. So starting with decay, you've got 1 dark matter particle in the initial state. If this happens at all, it has to happen with a very long lifetime. If dark matter is slightly unstable, the only way we'll probably ever probe that is through indirect detection, because it's certainly stable on the lifetime of a collider, or the time it takes to pass through a direct detection experiment. So the picture here is dark matter particle. You start out with a dark matter particle, then a miracle occurs, the new physics that we would like to probe. Standard model particles are produced. Those standard model particles subsequently decay into the long-lived stable standard model particles, and that's what we look for. The observable signatures are controlled by the dark matter mass and what it decays to, as well as the decay lifetime, which controls the rate. The rate is just proportional to the dark matter density because this is a one-body process, so if you're looking for decay, you want to look for regions where there's just a lot of dark matter. You don't care about how clumpy it is, you just care about the total dark matter content in this region. The other class of signatures that people talk about a lot is dark matter annihilation, which is just, okay, let's go to the next one up. Let's say there are 2 dark matter particles in the initial state. Again, Same process as decay. We would like to probe the new physics that couples the dark matter to the standard model. The way that we would do that is look for the long-lived known particles coming from this decay and try to reconstruct what is going on in this blue blob with a question mark. So here the rate's proportional to the dark matter density squared. The integrated rate from a region is proportional to average density squared in that region. That means on one hand you can get very large signals by looking at regions of large dark matter density, but it also amplifies the uncertainties associated with the dark matter distribution. So understanding the distribution of dark matter, which is interesting itself, becomes also critically important for indirect searches from annihilation. Whereas in the case of decay, the dark matter could be perfectly stable or could just have a very long lifetime, and we don't really have much guidance as to what the lifetime should be. In the dark matter case, there's a large class of scenarios where the annihilation cross-section is what determines the density of the dark matter in the early universe. If that's true, and if the dark matter was once in thermal equilibrium with the standard model and annihilation's depleted its abundance, that gives us this thermal benchmark cross-section about 2 to 3 times 10 to the minus 26 centimeters cubed per second, which is going to show up on all the plots that I show. This number has nothing to do with particle physics and has nothing to do with the model of how the dark matter couples to the standard model. It's essentially just saying that the mass scale should be somewhat smaller. It's essentially just set by the temperature of matter radiation equality and the Planck mass. It's the only parameters that go into this number. But if we say, all right, we'd like this to be a perturbative cross-section mediated by some particle, then you can infer the ratio of the mass and couplings of that particles, and if you have a roughly weak scale coupling, then you also have a roughly weak scale mass. So that's the WIMP miracle, as Nima mentioned. So I'll mention a couple of talks. There's a talk by Hongwan Liu in one of the parallels where he'll talk about a case where 3 to 2 annihilation actually is important, where you do have to consider the case with 3 particles in the initial state. And while you might think this WIMP miracle has often been used to say, okay, let's just focus on the 100 GeV region, but you can actually have much lighter thermal dark matter. You can push this benchmark down. You can have cases where it's natural to have thermal dark matter at much lighter masses. And you can see Berlin's talk about that. All right, so where should we look for these signals of annihilation and decay, these long-lived standard model particles? There's a wide range of possibilities. This is probably not a complete list, but these are some standard options. You can look at how much you would change the early universe if you have a steady flow of energy of standard model particles appearing apparently from nowhere in the early universe. That can modify nucleosynthesis, it can modify the cosmic microwave background. In the future, we might get probes from this from 21 centimeter emission. An advantage of this is that it's independent of the late-time dark matter distribution. A disadvantage of this is that it's independent of the late-time dark matter distribution. So you can't win by looking at regions where the dark matter density is particularly high. You get the constraint that you get. You can look at the dwarf galaxies, the dwarf satellite galaxies of the Milky Way, which will be discussed in these parallel session talks. The advantage of this is that they're relatively close to us, only a few tens of kiloparsecs away, and they have low background. The dwarf galaxies have a very high mass to light ratio. There's a lot of dark matter. There's not very much baryonic matter. You can look at the galactic center. This is in some ways the complement to the dwarf galaxies. It's possible that the signal there could be very large due to the dark matter falling into the gravitational potential of our galaxy. But the background is also very high. The picture here is a map of the Fermi gamma ray sky. The plane is very bright. Signals from, if you're looking for constraints, not signals, constraints from the galactic center are also very sensitive to whether the dark matter density profile rises steeply towards the center or not. From simulations, this is still an open question. You can look at the larger galactic halo. So outside the galactic center, this is a large area. It's as nearby as you can get. We're in it. But the backgrounds, again, can be quite complex, and the dark matter signal is broad and diffuse. You can look at other galaxies and clusters. Clusters tend to give very strong decay constraints. They have large dark matter content. You can look at clusters at different redshifts and thus use that to eliminate backgrounds. They're also for annihilation signals as opposed to decay signals. However, the signals from these clusters can be quite sensitive to how much substructure there is in them. We can look for dark matter subhalos, the little clumps of dark matter in the Milky Way halo that have not had any significant number of stars associated with them. For this, you need wide field experiments where you can do blind searches, but we have some of those. We have Fermi in the low energy gamma rays. We now have Hawk at higher energy in the gamma rays. You can also look into the extragalactic background light, just all the radiation that would have come from dark matter annihilation or decay in all halos at all times. So people have done, as you'll see in many of the parallel session talks throughout this workshop, we'll see examples of almost all of these. Rather than try to summarize everything, what I'm going to try to do now is just tell you where we stand with constraints on annihilation decay. What do I think are the strongest current limits? Here is the short version if you needed to leave or needed to fall asleep for the next 5 minutes. This is the key point. That thermal annihilation cross-section benchmark is getting pretty close to ruled out for dark matter masses below about 10 to 100 GeV, depending on the final state, if you don't annihilate entirely the neutrinos and if you don't suppress the cross-section in the late universe. So if you want light dark matter, if you want it to be thermal, you have to have some way to suppress the signal into electromagnetic channels at late times. For decay lifetimes, over an extremely large mass range, over about the keV to eV mass range, we can say that if all the dark matter decays, it does so with a lifetime not much shorter than 10 to the 27 to 10 to the 28 seconds. So this is 10 orders of magnitude longer than the age of the universe. If dark matter decays, it does so very slowly, although there are some little windows where it can be a bit faster. So let me now justify those statements. So the results that I'm going to show in subsequent pages come from a large range, come from a number of beautiful experiments. This is not an exhaustive list. I'm not going to go into the details of how all these experiments work. I'm just going to show you the output. I will note that, as we heard in the last talk, Voyager 1 is now on this list because it has a cosmic ray detector, and now that it's outside the heliopause, it can actually make nice measurements of low-energy cosmic rays that are harder to get when you're inside a solar system. All right. So there are it's helpful in indirect detection to think about two broad ranges of mass scales for dark matter, because they have fairly different phenomenology. If the dark matter is much lighter than a GeV, the standard model particles that it can annihilate into are fairly limited. It could generically, until it's lighter than an MeV, can always annihilate to electrons and positrons, photons, and neutrinos. If it's below about 100 MeV, those are the only choices. So this makes it relatively simple to ask, okay, how would we search for such light dark matter? As I mentioned, the cosmic microwave background in the early universe can set a strong limit on this. The mechanism here is that if you inject electromagnetically interacting particles during the cosmic dark ages, they ionize hydrogen. You don't need to ionize very much hydrogen to provide a screen to the CMB that will modify the results of Planck, because the CMB experiments are now fantastically sensitive to these things. So this first plot shows a result from a calculation I did last year. So everything above this red line is ruled out. You note the top of this plot for cross-section is 10 to the 26 centimeters cubed per second. So that thermal relic estimate I showed there is above the top of this plot. This is for annihilation into electrons, positrons, or photons. Those three lines show these different channels. So down here, you really need a pretty large branching ratio into neutrinos, or some suppression of the dark matter annihilation cross-section at late times, if you don't want to be ruled out altogether. If you do have a suppression of the cross-section at late times, the easiest way to get it is a velocity suppression. If the annihilation rate scales like b squared, these CMB constraints become weak because the dark matter is moving pretty slowly back then. You get stronger limits from measurements of the photon galactic diffuse background, and now measurements of cosmic rays by AMSO2 and Voyager. If we go up to heavier masses, to the WIMPs that Nima discussed in his talk, if you're talking about GeV to 100 TeV dark matter masses, there's a rich array of possible annihilation products. The generic way that dark matter annihilates or decays in this mass range is that it produces many standard model particles, many of them are quarks, they will hadronize. That hadronization process will produce neutral pions. Neutral pions decay largely to photons. So unless you have some symmetry that prevents this from happening, in general there are rich photon signatures in this mass range. The CMB constraints that I showed you earlier, they continue to rule out thermal relic cross-sections for masses below about 10 GeV, but above that point, those constraints can no longer limit thermal relic dark matter. So for photon-rich channels, you get significantly stronger limits than CMB from looking at dwarf galaxies. So this plot on the right shows a recent analysis of the Fermi collaboration of dwarf galaxy limits. That's the black line. You see that it crosses this dashed line, which is the thermal relic value. I mean, dark matter doesn't have to be a thermal relic, but it's a convenient benchmark to compare limits for a few tens of GeV for this annihilation to BB bar, which is an illustrative channel that produces a lot of photons. By the argument that I just made, a lot of the standard model channels look very similar in this way. If you have channels that produce copious amounts of electrons that will produce a spectral feature in electrons and positrons, AMSO2 measurements of cosmic rays can be very constraining. Likewise, the antiproton limits, which I'll talk a bit about later, are also quite powerful for hadronic channels, although those limits do have extra uncertainties associated with our not imperfect understanding of cosmic ray propagation. You can also have lines which are not a photon continuum from pi naught production, but essentially gamma ray lines. There are strong constraints on that from the galactic center for line signals you don't care so much about background. So this plot on the right was shown at ICRC by the Hess collaboration. That green line, that black line in the middle of the green is a projection, not actual data, but at ICRC it was said they're in the process of unblinding now, so stay tuned on that. At energies above about a TeV, for the continuum photon channels, Hess has done an analysis of the galactic halo, which sets stronger constraints than the Fermi Gamma Ray Space Telescope. And I think it's worth mentioning that at these high scales, you may look at this and say, oh yeah, but this is still way above my thermal benchmark. Well, A, dark matter doesn't have to be thermal. B, even if it is thermal, especially for heavy dark matter, there are generic effects at late times that can significantly enhance the cross-section, such as Sommerfeld enhancement or the formation of bound states. And we have a couple of talks about that in the parallel sessions. If we turn now to decay, and we ask again, let's look at the light decaying dark matter. Again, it'll decay to photons, neutrinos, electrons, and positrons. We could constrain that by the photon diffuse background in this MeV to GeV range, but actually between about 10 MeV and a GeV, there are now really excellent constraints from Voyager. So decades after it was launched, after it's left the solar system, this is now one of our best ways to constrain light decaying dark matter. Although there are also some stringent constraints from the CMB and the early universe. So you can see the lifetime limits here. In general, we can probe, for light dark matter, we can probe lifetime limits between about 10 to the 25 seconds and 10 to the 27 seconds, depending on the channel that it goes to. If they're photon-rich channels, the photon diffuse background is most efficient. If you're producing a lot of electrons, then Voyager and the early universe provide the best constraints. If we now move up into the WIMP region again and ask what would it look like if a WIMP was decaying, there's a recent analysis by Cohen et al., which summarizes a lot of different limits, and essentially they show that you can rule out lifetimes of 10 to the 27 to 10 to the 28 seconds for dark matter masses in the range from about 10 GeV up to 10 to the 10 GeV. So heavy dark matter, if it decays at all, is doing so pretty slowly. Now, there have been caveats to most of what I've said so far, which is I've assumed that you make photons, or electrons, or positrons, or protons and antiprotons, something that you can see in these telescopes. Of course, you can also produce lots of neutrinos. In that case, these neutrino experiments have unique sensitivity. So these are some recent results taken from talks at ICRC 2017. You see, so the orange line on this left-hand plot is the constraint on neutrinos from super K, from mass scales, from super K and ice cube, from mass scales from a GeV up to tens of TeV. And the neutrino experiments really don't have a lot of competition, especially in the lower end of this mass range, if the dark matter annihilates primarily into neutrinos. At sufficiently high mass scales, they can also do better than constraints from gamma rays from Hess and Veritas, although perhaps that will change as we get more results from Hawk. So that's what I wanted to say about the status of constraints. We light dark matter. If it's thermal, the cross-section has to be suppressed at a late time. Above about 10 to 100 GeV, we are not yet at the thermal relic cross-section, except possibly at high masses where other non-perturbative effects like bound state formation or Sommerfeld enhancement become important. So, do we have hints of signals in the data? Well, most of the data that we've seen, there's not much in the way of hints of signals. You get nice, clean constraints. But there are some exceptions. So here, these will all be discussed in more detail later on, so I'm just going to give introductions. The 3.5 kV line will be discussed in a plenary by Ezra Bulbul. She was one of the discoverers back in 2014 when they found this signal at roughly 4 sigma significance. Since then, that was in a sample of stacked galaxy clusters. This plot is from a review article by Kev Abazagian. that came out earlier this year, and each of those contours that doesn't overlap with 0 on that plot corresponds to another detection of the 3.5 keV line in another system. So at this point, it's been seen at the center of our galaxy in a range of different clusters, and also in recent observations from the Chandra Deep Fields, which I think Ezra is going to talk about in more depth. There is a possible dark matter explanation for this, which is fairly simple, which is that it's a roughly 7 keV sterile neutrino decaying into photons. It's a very simple model. It's a very predictive model. Because it's very predictive, it's very testable. You can go and look at the signal from any system, as we said in decay, should only depend on the amount of dark matter in this system. So you can test this by looking at objects where we'd expect there to be dark matter and see it decaying and see if we see anything. So there's some tension between this simple dark matter decay explanation and observations of dwarf galaxies, stacked galaxy clusters, and M31. Now, this tension could be alleviated if you have a somewhat more complicated dark matter explanation. But I will leave it to Ezra to talk about this in more depth. The one thing I want to say is that of all the excesses I'm going to mention here, this is one where I think there is actually potential to test the possibility of a dark matter origin in the near term. This first plot on the right shows you the current X-ray constraints on sterile neutrino decay. This is expressed not in lifetime, but in the mixing angle, but the lifetime's around the 10 to the 27, 10 to the 29 second region that we've been talking about before. So these are limits from New Star. You can see that data point up there is the 3.5 keV line. So it's right on the edge of the constraint, but it's maybe still okay. If the difficulty here is that we believe the line is there, but it's hard to separate it from possible astrophysical backgrounds, then one strategy is to seek experiments with good enough energy resolution to both separate the line from the astrophysical backgrounds and to probe the velocity distribution of the dark matter in the galactic halo. Because if you can see the Doppler shift due to the motion of the dark matter in the halo and the resulting line broadening, then that would be a fairly smoking gun signature of a dark matter origin. One experiment, unfortunately, Hitomi, which did have this angular resolution, failed after only a few days of observation. But one possible future instrument that does have this angular resolution is the Micro-X sounding rocket, to which I refer you to this paper for more information. They think that they can get energy resolution of only a few eV, and they have a dark matter flight planned and scheduled for 2019 at the moment. So keep an eye out for that. The GVXS, my collaborator Mariangela Lisanti is going to, has a plenary talk on this and other gamma ray signatures in the sky later on, so I'll just mention briefly what you need to know about the GVXS. It's a glow of gamma rays at the center of the galaxy. It peaks at 1 to 3 GeV, hence GVXS. It's roughly centered on the galactic center. It looks spherical. It looks steeply peaked towards the center. It looks very much like a signal that you would expect from thermal dark matter in the 10 to 100 GeV mass range, annihilating into photon-rich channels with a steep dark matter density profile. There have also been claims of faint hints of possible corroborating signals from 2 dwarf galaxies, Reticulum 2 and Tucana 3. However, the consistency of these 2 depends strongly on how much dark matter there actually is in those dwarfs, which is not very well known because they're ultra faint. There have been several studies that I and others have done that suggested hints that this does not come from dark matter, that it comes from some novel population of sources, or some stellar population around the galactic center. There will be discussions of that in the parallel sessions too. There are also a couple of remaining outstanding constraints in cosmic ray data that we don't understand, beyond the questions of cosmic ray propagation that were discussed in the last plenary. AMS-02 has produced beautiful antiproton data, and there have been claims by a couple of groups that the error bars on that antiproton data are now small enough that there is a hint of a 4 sigma signal in the antiproton data. So that's plotted in these lower 2 panels. There appears to be a small bump, a small excess at around 4 sigma significance. However, I should say, as always, I mean, the background modeling is always a difficult problem here. So there may be systematic uncertainties that are larger than that. Again, similar to the GVXS, this prefers a tens of GeV to 100 GeV dark matter particle annihilating with a roughly thermorelic cross-section, and so the 2 are broadly consistent. So again, this is something to keep an eye on. But as we heard previously, modeling of cosmic rays is challenging. Modeling of the production cross-sections here is challenging as well, but it's interesting. In AMSO2 positrons, we have an excess which is much larger than 4 sigma. It's been established that AMS sees a large excess of positrons above 10 GeV. It's been extensively discussed as a possible signature of dark matter annihilation or decay, and there's a talk here about that. I just want to point you to, there's been recent results that the Hawk telescope has detected extended gamma ray emission around 2 nearby pulsars, and there will be talks by my session chair, Tim Linden, and Dan Hooper in the parallel sessions about using this as an experimental probe to try to understand the electron and positron spectra from these pulsars, and use that to constrain the contribution to Vermeer. So I think this is great. This is a new experimental handle on the positron excess, which has been very puzzling since more or less my first TeVPA back in 2009. In the future, we need to get better at, so what do we need to do better indirect searches? We need to be better at modeling the signal, at understanding how the dark matter is distributed. We need to be better at so there are talks about this, which I'll just wave to since my time is up. We can get better at modeling background. In the gamma rays, that means both understanding the background from first principles and developing more data-driven tools for parameterizing the background, which will be discussed in these talks by Porter and Calore. We have the first results now emerging from telescopes like Dampi and Callet, which we'll hear about later at this conference. There are many future missions. I cannot possibly list all the future missions that might shed light on dark matter, but here's a set of examples. The CTA will probe the high-energy gamma ray band, will improve on HESS and Veritas, and MIGO could potentially get into that MEV to GeV range that I told you was quite hard to constrain. GAPS will probe cosmic ray antideuterons. CMB stage 4 and 21 centimeter experiments could open a whole new window on the early universe. Since I'm at like minus 30 seconds, I will just leave my summary slide up there, and thank you all very much for listening.
Thank you. Do we have any questions? Feel free to walk up to the speakers there. Anyone? So I have one question. What is going to be the critical, when you think about all of the indirect detection signatures that could be dark matter or it could be something else, to what extent are different things going to be about statistics, and to what extent are they going to be about systematics? Right.
Well, okay, so that's, yeah. I mean, it really depends on the channel that you're looking in. I mean, we've seen, right. So we've seen that with the galactic center excess, there you have something that the statistics are enormous. It's entirely a question of systematics, of figuring out whether it is dark matter or not. So, but you might, so to the degree that like in the Fermi energy band, you're probably not going to have a whole new experiment that does dramatically better than Fermi. It's probably unlikely that we will see more excesses like that in that energy band, for example, where it's 50 sigma or something. I mean, if there are 50 sigma things in Fermi data, we would probably know about them by this point. So but there are other signals in Fermi data, such as in the dwarf galaxies, where it is largely a game of statistics at present. You have these potential signals that are 0 to 3 sigma, depending on how you do your statistical analysis. So, I mean, so as new experiments turn on and cut into really new regions of parameter space, I mean, if they're sufficiently large improvements over the previous experiments, you could start seeing things like the GeVXS. But I think the more likely thing that we will see is you have 2 and 3 and 4 sigma excesses, and the question then is, well, it's a combination then. More statistics would certainly be helpful, but you have to understand, if you've only got a 2 or 3 or 4 sigma excess, you have to be very sure that there are not systematics which are constraining things at that level. And systematics here don't usually mean systematics of the experiment. They mean systematics into, and I talked very little bit about this, I waved you at some parallel session talks. They mean things like, how do you model the background for the 3.5 kV line? How do you understand charge exchange reactions? How do you, for particles, for the antiproton case, how do you understand the true systematics in the cosmic ray propagation uncertainties and in the production cross-sections? Some of these can be probed by terrestrial experiments. I mean, like we could try to do better measurements of production cross-sections and so on. Some of them will probably need new ideas. I mean, It's possible that we have a signal where there are essentially no systematics, like we get more dwarfs and we see a gamma ray line showing up at 1 to 2 sigma in a lot of different dwarfs. At that point, you probably just need more statistics, but I think in general it'll be an interplay.
Alex?
Thanks, Tracy. I was wondering, for something like Amigo, can you discuss a model that evades the CMB constraints that you showed earlier, but would be detected by an MEV gamma ray emission?
Yeah, well, so the usual trick to play if you want to evade the CMB constraints but still have a signal in the present day, there are a couple of things you can do. So, I mean, velocity dependence helps to some degree, because at the CMB, the dark matter is typically moving very, very slowly, while in the present day you have dark matter in bound structures, so it can have a higher velocity. But I mean, if you think that's what's going on, then it does change your detection strategies, because you want to look at the systems where the dark matter is going very fast. You can have variations on that where the dark matter is annihilating against something which is present in the early universe, is all gone by the time of the dark ages. But then it is repopulated by some late time decays or some late time process. So I mean, like, this can be the case in models of asymmetric dark matter, for example. So yeah, so there have been some studies on how well Amigo can do in the case of specific models, and I'm not an author of those studies. So I mean, there is this tension that you do have to find a way to get around the CMB constraints. But present-day galaxies and present-day halos are a pretty different environment to the universe at redshift 500 or 600. So, there are always going to be ways to kill the signal in the CMB and still have a substantial signal here, most easily by velocity dependence, but also by, essentially by time dependence.
Anything else? If not, let's thank our speaker again.